So this talk is going to give you a brief idea about how OpenMP can be used for not only HPC but also for on embedded platforms where you have resource constraints, you don't have that much memory or that many cores, so you don't have the luxury to oversubscribe resources and things like that. So we are going to look quickly into why is this work important. So this particular slide shows you from 2000 until date, how the hardware have evolved. In the sense we started off with single core systems, homogeneous cores, and then we went all the way until today, 2015, where we are seeing cores which are heterogeneous. We have systems with ARM cores, DSP cores, and we have Qualcomm Snapdragon kind of cores. And we have co-processors from Intel Xeon Phi and this Mainz Landing, which will be out, I think, in summer 2016. And we have Jetson TK1 from NVIDIA, which got ARM and GPU cores. So it's no longer homogeneous CPU cores, but we are seeing lots of heterogeneous systems and CPU plus something else. So although it looks cool, the question is how do you program these fancy devices, right? What's the right technique to do the programming? So before we get there, I wanted to show this cool picture, which is from GTC 2015, I think, where the NVIDIA CEO drives on to the platform, with an RD Connect, which has actually got an NVIDIA Tegra TK1 ARM plus GPU in it. So it was pretty fascinating when he comes on the stage for a few inches in his RD Connect card. So it's embedded systems, right? It's cool. It's a lot of fancy, cool devices, sophisticated devices. So how do you program this magic device? So the challenge that we are seeing in the embedded platform is that it's most of the proprietary tool sets or programming environment you have is too tied to the hardware. So if you take Texas Instruments or Qualcomm or one of the semiconductor companies, you would see that they have a tool set, but that tool set only talks to its own hardware. Right? If you take that particular tool set and try to program on another platform, even belonging to the same family of the vendor, it may not work. So you might have to redesign something. So that makes the whole programming a big issue, where people like developers and programmers spend too much time on low-level details and trying to crack open the hardware and trying to find out what's the software toolchain. We do not write once and use it everywhere. We write once and we never reuse it because the platform changes, right? So there is a lot of engineering effort and there is a lot of time-consuming effort going on. So high time-to-market solutions, meaning the time it takes for the product to go to the market becomes longer because we need to refactor or redo the codes, because it doesn't work for more than one device. So there is high TTM. So bottom line is we have these cool devices, we have proprietary tool sets. How do you actually look into building this kind of an industry standard, which has programming models, which is run by industries, academia, universities, but it's a standard programming model, and you use that on multiple platforms in order to gain some portability aspect, right? You want to have a performance portable code. So the reason behind using industry standard is to offer a portable software solutions and be able to target more than one platform. Take TI, take Qualcomm, take FPGAs, take ARM plus GPUs, take NVIDIA. You want to write once and be able to use your code multiple times. So that's diving into OpenMP. So folks who are working on OpenMP might be pretty familiar with this slide, which is from Jim Cowney's OpenMP, as I see 14 actually is from his BOF OpenMP session. So we see how the standard has evolved from 1997 through 2014, and it's still evolving. So this is where it got started, and OpenMP also started supporting accelerators since 2014, and now they are moving on to OpenMP 4.x and 5.0, talking about a lot of cool new features and things like that. So it's been evolving, multiple vendors, lots of people using it, and it's gained a lot of traction. So quick look into how the OpenMP implementation itself works. The beauty of OpenMP itself is you plug in directives, you don't change the code. So you just need to use the C code or Fortran code or C++ code you have, and you just need to know the kind of pragmas you need to use, which is where you have so many OpenMP tutorials and things where they teach you what kind of code, what kind of pragma you should use. And you plug it in, and the compiler produces sort of a translation, where the compiler is a magic compiler here which does all the crazy things under the hood. and you get a code that you're able to port on several platforms, plus you're able to run it on multiple cores, not just a single core. And there is this runtime component which does all the scheduling of tasks, moving work units to different cores or different platforms and things like that. So we have OpenMP, which is great, an industry standard, which we could definitely use. So this kind of talks about, we have OpenMP, great, we know it works, awesome. We have tons of publications, tons of people working on it. So what is it that OpenMP needs to do more, or what can be attached to OpenMP, or what can OpenMP be translated to in order to make it even work on embedded systems as well? We know OpenMP is fabulous on HPC, so how to get that to work on an embedded platform, right? So this particular slide just tells you that we have these cool state-of-the-art models, but sometimes when you're talking about an embedded system, your phone, which has got a GPU card, or it's got these Apple processors, has these M9 co-processors, which is the one behind all your cool things in your Apple apps actually. So there are these co-processors, they are not CPUs. So there are co-processors, or there are systems which may not even have an operating system, right? It might be bare metal. So how can OpenMP talk to a platform which doesn't have an OS? It's bare metal. So how do you get OpenMP to talk to it? So diving into yet another standard, which is put together by Multicore Association. That's the link, and I can give you the slides if you're interested. So Multicore Association is basically a standard programming model again, and there are more than these listed over here who are members of Multicore Association, including University of Houston and University of Delaware will also become a member of MCA soon. We have Texas Instruments, Qualcomm, Siemens, etc. So what do these guys do? We know there are issues, programming aspects for embedded systems. So what do these guys do? Is they have created APIs that will help you manage the resources underneath, say 4 ARM cores, 8 DSP cores, 4 GPU cores, or any sorts of those specialized accelerators, and be able to communicate across cores, across 4 ARM cores. Again, if you have a platform, you have 4 ARM, you have 8 DSP. How do you communicate between those two different type of platforms? So you will be able to communicate with the MCA APIs, and tasking, which is becoming so famous a programming model these days to be used. So MCA has come up with a task parallelism kind of an API, which allows you to create, initialize, schedule, analyze dependencies between tasks, and make a task parallelism, explore task parallelism of your code, and be able to put that on embedded systems. So what did we want to do in this research? We know OpenMP exists, we know MCA standard exists, both are cool industry standards. So what we wanted to do is, somebody should be able to take an application written in OpenMP, which we know is easy, and we wanted to translate OpenMP to the Multicore Standard Association API layer, which gives you the vocabulary to communicate and manage and explore tasks underneath, and on a platform which maybe has an RTOS, which maybe has an Linux OS, or it might be no OS, it's just bare metal, and then you could target the underlying platforms, which could be anything. So this is our software solution stack: OpenMP, MCA, and the target platform. Then how did we do it? So this talk is going to focus on the task parallelism, but in the past we have used the resource management as well as communication management APIs of Multicore Association and performed some successful translations and published in IPDPSW workshop and TechCon and LCTES, etc. So I'm saying this because if you find such a talk online, you need to know the difference between what was done in the past and what we're talking about now. So diving into the Multicore task management itself, so this is what I was talking about. You have an application, you could write an application in MCAPI itself. MCAPI could be your starting point, and MCAPI API is going to spawn lots of tasks, and it has this MCAPI runtime layer, which also coordinates with the communication API and the resource management API, and you have cores of type A, cores of type B, cores of type C. So this is what the MCAPI is trying to accomplish. You have varied type of cores, and this is task parallel programming model. You start a code written in MCAPI. How do you literally translate and go down to your target platform? So overview of MCAPI is basically it's an industry standard contributed by lots of industry, and Siemens, Germany has a major role to play in this MCAPI. They were leading the MCAPI group along with University of Houston, Qualcomm, Texas Instruments, and several other folks. It's scalable. And MCAPI specification is designed in plain C, so you could build it on top of any kind of OS or even bare metal. The implementations that you will find online are the ones from our University of Houston MCAPI implementation, which is open source, and there is a GitHub available online. If you don't find it, again, write to me, I will find you the right link. There is another open source implementation that Siemens came up with, and it's part of their larger product, EMBB. So these are the two implementations out there. So a little bit about the MCAPI features itself. You have tasks, you have queues, and heterogeneous systems is what we saw, right? We have cores of different types. And the tasks are, queued upon in different queues. You have local queues, global queues, and depending upon where your cores are, the cores kind of take tasks from each of the queues assigned to all those different platforms. So the critical thing here is to know that these are the terminologies for MCAPI. There is a job, there is an action, and there is a task. Meaning, you could every MCAPI job is describing what is the work that you're doing, which is technically your job, plain and simple. And action is basically, it could be a hardware action or it could be a software action. One job can have multiple actions, which means an action can go on core type A, action B can go on core type B. So you have multiple actions, one job, and several different platforms you can target. And task is, we already know what a task is. It's a lightweight operation with fine granularity. So we kind of experimented two approaches, using MCAPI as a standalone implementation, as in the programmer writes a code using MCAPI, A, and B, you write a code in OpenMP and translate that to MCAPI. So quickly, let's look into how both of them fared. So this might look overwhelming, but the bottom line is just a structure of how do you create tasks and how you start assigning it to the cores, how do you schedule them, and what sort of scheduling algorithms you can employ, when does a task get finalized, when does a task get killed, and when do you start moving things around, and that's the structure flow. So if quickly, if we go through initialization, you create a job, action, you create a task, you wait for the task, if it's performing something, if not, you switch to another task, so on and so forth. And there is an MCAPI layer basically because in your embedded systems, you're going to have cores of two types, right? ARM and GPU. So how do you communicate between ARM and GPU? You need a communication layer. So this could be your host core, which is your CPU, and that could be your GPU, ARM plus GPU. So you're communicating between both the layers. The platforms that we use to test are a simple Intel platform, 8 cores, to make sure that our prototype implementation was actually working before moving on to the embedded systems. And we also tested it on an NVIDIA Jetson TK1, which got 4 plus 1, quad-core ARM Cortex, and a Kepler GPU with 192 CUDA cores. The compilers for both the platforms respectively are x86, GCC and MDCC versions, and the benchmarks that we tested are Rodinia benchmarks and Barcelona task benchmark suite itself. The reference implementations themselves are Siemens MCAPI, GNU's OpenMP implementation, as well as I think one more thing I missed here was OpenUH MCAPI implementation. Okay, let's look at some results. This is the last few slides here. So standalone UH MCAPI evaluation was the benchmark that we used versus sparse LU. So when you look at the graph, is you have 16 threads here, you have 4 cores or 4 threads here. This is your Intel platform, virtual 16 cores, and then you have 4 ARM cores. And the gray scale here is your GCC, the GNU OpenMP task implementation, Siemens MCAPI and UH MCAPI's implementation, 2 different types of scheduling. So we see that even after introducing the MCAPI layer, we don't see an overhead compared to GNU's OpenMP task implementation, which is good news because now you can play with it even more. And this is even better because Siemens MCAPI still does not have the vocabulary to communicate between 2 different type of cores, and that's why you see a bit of a dip here, and I'm sure they're working on it. And we have GCC OpenMP and we have UH MCAPI, both the scheduling platforms. And GCC OpenMP here is available as part of the Jetson TK1 software. So I believe it's a fine-tuned OpenMP task implementation because it's part of the Jetson TK1 software package. So comparing that against our own UH MCAPI, which is pretty good, again, you see, good speed up versus serial code, and we don't have an overhead because we introduced the MCAPI layer, which means, it was worth the prototype implementation. So this is the picture that I'm trying to show, where you have a job and it could have two actions. One action could be a CUDA node, one action could be a coprocessor, or what have you. So the action could be anything. It doesn't need to be a CPU action per se, which is the beauty of using tasks, MCAPI tasks on different type of platforms. So this one is talking about, so why do we have this, right? What's the significance of this? So we use the MCAPI implementation, and we created several different approaches. So one approach was vanilla CPU sequential, which is your gray bar. MCAPI CPU, like MCAPI's one action is going to CPU, MCAPI's two actions, one is going to CPU and one is going to GPU, and MCAPI's single action to GPU, which means MCAPI's translation to CUDA actually underneath. So obviously CUDA does the best. We all know CUDA does the best on NVIDIA GPUs. So this picture was to show that although we don't see a great speed up using MCAPI GPU, but you could call a CUDA action using an MCAPI action, which means you could call any other action, which doesn't need to be necessarily a CUDA action. A CUDA action works on a GPU, but it could be a DSP action, which could work on a TI platform, so on and so forth. So this is a graph to just show that it works, MCAPI, different actions on different platforms. It's a working prototype. So far we only saw a code that was written using MCAPI. This one is, okay, so MCAPI is still a low-level API. How do we abstract it even further? So why can't I write a code in OpenMP, right? We have used OpenMP tasks, which is definitely an easier way to program a task-based application. So why don't I use an OpenMP task-based programming model and translate that to MCAPI, which we saw works, and try and implement that on the same different platforms. So to give you a brief idea, so these are the tasking constructs and APIs and group constructs, etc. So that's the picture I wanted to get to. So you have an OpenMP application, the compiler translates that, and it's actually the compiler. It's also building it with the MCAPI runtime library, which is the one that we designed. And eventually you would see that it gets linked and there is an executable created for the type of the platform that you're targeting for your OpenMP application. So compiler front-end translates OpenMP into MCAPI function calls. You implement MCAPI function calls and convert OpenMP tasks to objects. And then you do the linking eventually to get your executable. So quickly looking at the evaluation of an OpenMP translated MCAPI implementation. We see a libcom RTL and we see an OpenMP translated MCAPI RTL, and we actually see the green bar doing better at times compared to the purple bar, which is your OpenMP implementation. Again, a point to note here is that this translation did not cause overhead, and we evaluated that using EPCC's OpenMP micro benchmarks, if you know about that. And we see number of threads, it's also scaling pretty well. So the bottom line is, there was no overhead and you were able to use an OpenMP code, which is easier to write and things. Okay, so to conclude, what we do was we wanted to explore task-level parallelism for embedded platforms. So we created a task-based implementation. Goal was to use industry standards because you want to be able to program better and not go too low level and abstract low level details at the programmer's level, right? So we did this, used industry standards MCAPI, translated OpenMP to MCAPI, which is even better. Both are industry standards. One is high level, one is comparatively low level. So further abstraction because you plugged in an OpenMP level, easier to program, less tedious, faster software development time, obviously faster TTM. Your program managers are happy because the product is out in the market faster. And you code once, you use multiple times. That's the reason why I showed the MCAPI action could be spawned into a CUDA node or a CPU node or a DSP node. So that's the beauty of writing once and using it multiple times. And we targeted on more than one platform, so it was good to see that it's not just Intel, but it could also work on ARM plus GPU. Comparable performance and lesser to no overhead, and this is published in the IEEE HPCC conference. And if you look into OpenMP MCAPI online, you can find the paper. Just write me a note. So yeah, that's what I got. Thank you for listening. You take questions.